right, cool. So I'm going to be using the iris data set. Are you familiar with the iris data set?
Yeah.
Yeah, it's kind of a famous data set in like the like machine learning world. Sklearn datasets load iris. Cool. Then I'm going to do my train test split. So I'm going to be kind of skipping all the like EDA stage just because I want to go into the modeling and the explainability part. So import in this train test split library. And then do my train test split. And I'm gonna do my test size to be 0.2. It's not too important, but my X is gonna be the iris. I believe it's data. Yeah, data. Iris.data, and then my target is gonna be iris.target. So done my train test split. I just want to do a little sanity check. Y train.shape and y test.shape. So I'm going to be training on 120 examples and testing on 30. Not the biggest data set, but it'll do for this example. And then I want to use a random forest. I'm going to use classifier. So I'm going to grab an instance of it. I can never remember how to import it in. Import. And make my classifier, random forest classifier, and fire that up. So first I'm going to train it, which is fitting, and X train and Y train. So I fit it. I want to see how I did now. X train and Y train. See how we did on our training data. Then I'll see how we do on our testing data. I want the CLF dot score. So 100% accuracy on our training data. That's usually a bad sign that we're overfitting. Y train or Y test. Sorry. 100% accuracy on our testing data as well. Well, we only have 30 examples here, so on our test data set. So I guess that's not too out of the ordinary with a random forest. But usually if you get 100% accuracy on something, especially your training data, that's usually a red flag. You're way overfitting. So if I want to know some interpretability about this algorithm, I get 100% accuracy, but like, why do I get 100% accuracy? So let's first look at random forest as feature importance. So these are the different important features and their importances. So I'm going to plot that out. Size equals 12 by 8. I want to do a plot.bar, and X is going to be range length of this, and then the height is going to be, oops, height is going to be this. You need to import matplotlib.
So, and quick question.
Yeah, go for it.
So for the feature importance, it was just an array with 4 values. So So we're only using 4 values right now, or we're only specifying like for the top 4?
Yeah, that's a great question. So let's take a look at what our training data is. So yeah, it's only 4 features. And if we look at iris feature names, so there's sepal length, sepal width, petal length, and petal width. So these are the 4 features that we're using to predict what type of iris it is. So yeah, just 4 features.
Okay.
So then let's take a look at what these features are actually. I'm going to change the X ticks because right now they're just 0, 1, 2, and 3. I'm going to change them to be the actual columns. And I want iris.feature names. So now the most important feature in predicting irises is petal length and petal width. These are the most important, then sepal length and sepal width. So we know that petals are more important than sepals. I'm not a flower person, so I don't really know what the difference is, but if you were like, maybe on your data set, it might be a little bit more interesting. So this is called global interpretability. I think they go over a little bit of like feature importance in that curriculum. Does this make sense so far?
Yeah, so pretty much after running the fit on the train and the test data, it's looking at which features were able to help best identify what was going to happen with the prediction.
Yeah. So in general, this feature is used most often inside of all the decision trees inside of the random forest. So this is a really important feature. Then this is the second most used, and the third, and the fourth. So this is the most important feature in predicting the flowers. Then this is the second most, the third most, and the least most.
Okay.
So this is called global interpretability. There's another thing called local interpretability. So let's say I have this is an example in my X test. I have a flower that has a sepal length of 6.1, a sepal width of 2.8, a petal length of 4.7, and a petal width of 1.2. My model is going to predict it to be, so if I do clf.predict, and I put this in there, I'm going to get it there. Scikit-learn does not like it when you put in a single sample. So I put in a single sample. So this is a single sample. So it kind of tells you what to do. So you can just copy this. That's a single sample. Dot values, and then paste that. And, oh, I don't need the dot values. So it predicts it to be class 1. Iris dot target names. So class 1 is a versicolor. So it predicts it to be a versicolor. And if we take a look at what the actual value is, it's class 1. So it got a correct prediction, but why does it get the correct prediction? It's kind of hard to say like why it does, because we know that petal length is important, but petal length of 4.7, is that what does that really mean? So to know like understand like what a single prediction is giving you, this is called local interpretability. There's a library called Line that I like. This is like using text data. They're predicting whether the person in the email was a Christian or an atheist, and it looks at like different words. We're not doing text data. We're doing like a tabular data. So if we're predicting whether a mushroom is poisonous, we know that the odor is foul. This leads to it adds 0.26 to the probability or the chance that it's going to be poisonous. If we know that the gill size is broad, this decreases by 0.13 the probability that it's going to be edible or poisonous. And then this stalk surface above ring equals silky, that makes it more on the poisonous. So it tells you like what each feature is, how they contribute to your prediction. So in your case, it would be like maybe education being grad school increases your chance of making more than 50,000 by this amount, and then by having capital losses of this amount, it decreases your chance of having a salary above 50,000. So this line I think is pretty cool, because you can kind of get a little bit of an understanding. So I'm going to really quickly show how to use Lime. We don't really teach it in the course. So import Lime. You will have to, if you want to use this, you will have to install it because it's not in the learn.co package. I'm going to use Lime Tabular. Lime tabular. So I put in what I trained on. I put in what my features are. In this case, my features are the iris dot feature names. I put in what my target variable is, my class. Iris dot target names. And this this variable right here, if you're working with continuous variables, you have to set it to equal to true. They go a little bit more into it in the documentation. I can show that to you after this. And that's not what I was hoping for. I want feature names, not features. So nice, no errors this time. That's always good. So now I got this explainer variable. I'm going to make a new variable using this explainer.explain instance. So I want to explain why this instance, why having a sepal length of 6.1 and a sepal width of 2.8, why does our model predict it to be a class 1? So I want to grab that variable, which is x test 0. I put in my predicted probabilities for my random forest. Predicted probability equals 2, top labels equals 1, and then show a notebook. So for this specific instance, it predicted it to be class 1. And reason it predicted it to be class 1 is because this versicolor, that flower, when the petal length is less than 4, this is interesting. So this looks like this would be like a greater than and equals, because the petal length is 4.7, so it is greater than 4.2, or it is between 4.25, and I wish they wouldn't have cut it off. But it looks like it's supposed to be between that, so that's why it predicts it to be, this predicts it to be positive, and then the petal width, which is 1.2, is between 0.3 and some other value. So it didn't end up being very cool because I don't know how to pull all of this out because it's cutting stuff off. Let's do another example. See if there's like a better example. Do the second example from Xtest. So this one it predicted to be a setosa flower, which is class 0, and looking at the actual prediction, it was correct as well. And I guess all of them should be correct because there's 100% accuracy. But so the petal width on this one, let's look at Xtest 1. Petal width is 0.3 on this one. So the petal width in this case is less than or equal to 0.3. So when flowers have a petal width less than or equal to 0.3, it thinks there's a good chance it could be a setosa. It bumps that up. And when the sepal width is greater than 3.4, it thinks there's a chance it could be a setosa as well. So it kind of gives you it kind of gives you a little bit of an understanding of what's going on under the hood. It's certainly not a perfect library, but I think it's better than a lot of like the local interpretability libraries that I've seen.
Oh, so it pretty much just breaks it down into, right, these are the probabilities of it being one or the other. And since this model had an accuracy of 100%, and that's why, so I'm just going to use annotate real quick. But that's why this is always coming up as 1 instead of some percentage lower than 1.
Well, so with the random forest, these predicted probabilities, it's always going to get it correct. So it's always going to get, if we get 100% accuracy, what our prediction and what it actually is always going to be correct. These predicted probabilities are not always going to be 100%. So it's going to make the prediction on whatever of these 3 categories has the highest predicted probability. So if the predicted probability of Setosa was 0.8 and versicolor was 0.15 and Virginica was 0.05, it would predict it to be Setosa. So it's going to choose the overall random forest is going to choose whichever one has the highest predicted probability. So it doesn't necessarily have to be 100% for it to predict it to be a certain class.
Okay. So what if we were to change the means or the method used in the random forest? Because by default, because we talked about it before in class, but I think what was mentioned is by default it uses entropy instead of the Gini index.
Yeah,
is that right?
I believe that's right. We can take a look though.
Okay.
Yeah,
so
the criterion is Gini, so we could use. If we change stuff up here, you wanted to use entropy.
Yeah. So I'm just curious how it would affect everything below, whether it would still have the same level of accuracy, and if the interpretability would be the same.
Yeah. So you can change any of the hyperparameters as long as you've still put in the same, this right here, you'll still get the same. It'll still work. Let's try and change them so they'll be like less than 100. So let's do like entropy didn't have any impact. Like entropy and Gini index are usually pretty similar. Let's do like max depth. That usually will have let's just set the max depth where it can only be 3. And now we still get good accuracy. Max depth can only be 2. So now we get 96% accuracy. We run everything else. So it still predicts it to be it's still predicting it to be class 0. But so in this case, it thinks there's an 80% chance it could be this one, a 16% chance it could be this one, and a 0.03 chance it could be that one.
Okay.
So yeah, as you change these different hyperparameters, it will have an impact on this. So you typically won't want to do this process until you've gotten to the point where you've gotten the best results that you can, either through checking a bunch of models or tuning your hyperparameters.
Okay. And for this one, you use the random forest classifier in scikit-learn to evaluate which features are the most important.
Yeah. So a random forest classifier has the feature importance. So not all algorithms have it. I thought I read somewhere that they're changing that in scikit-learn. But like, this is a logistic regression cycle. Yeah, they get like predicted probabilities with no feature importance. So if you look at like random forest or any tree-based model, if you look at the methods, they'll have a feature importance. No, it doesn't have one either. Feature. Yeah, so I guess it's an attribute, feature importances. So it's an output. Man, let's take a look at logistic regression again. Yeah, so there's no feature importances in the attributes. So like a decision tree has feature importances, but you can kind of get feature importances from logistic regression based off the coefficient. Whatever has the largest coefficient is usually your coefficient with the highest magnitude, usually your most important feature.
Oh, okay. Oh, but what I also noticed was as you were setting up the random tree, so the decision tree classifier, is you didn't have to standardize the data. Like, so is that, yeah, so is that just the nature of that data set? Like everything is relatively low in magnitude that you don't have to scale it, or is
Yeah.
it?
This is a good question. So some algorithms do require like scaling. So like k-nearest neighbors definitely does, where you're checking like distance. So there's no like distance-based algorithm in this random forest or in a decision tree. So scaling is not required for like scaling on like a tree-based algorithm. It's a non-parametric. It's not assuming there's a specific shape on your data. So not required.
Okay. So if you was to do this using PCA, for example, like how would that look like? Would the process be similar, or?
So with PCA, you lose your features. So it's instead of petal width, we have PCA component 1 or PCA component 2. So I wouldn't recommend doing this with PCA because letting us know that PCA component 1 has increases your probability by 0.35 doesn't really tell you anything.
Okay.
So like it's the important thing is like knowing what feature has the impact on your target variable.
Okay. Yeah. So right now it sounds like the main one that would give us some level of global versus local interpretability would be random forests and maybe decision trees. Is that correct?
Yeah. There are some other libraries that can get you like global importance. So there's what is it called? Permutation importance. Where's the library? So this will get you feature importance. They use random forest classifier here as well, but you can use it with other algorithms to get like what's the most important feature. You don't necessarily have to use a tree-based model if you want like global interpretability, but it's a little bit easier just because you don't have to like start importing in multiple libraries to help you out. There's this really great Kaggle course. It's free, machine learning explainability. But we have 2 weeks off over the next after this week, so it might be kind of worth kind of playing around with. They don't go over Lime, unfortunately, but they go over permutation importance, partial dependency plots, and SHAP values.
Okay. Let's see. So I'm just taking note. There you go. So how would you use, say, like another method, like say, for example, k-nearest neighbors or even PCA? Like as you go through, and like when or where would you use it? Like dealing with a data set like Iris.
So PCA, as I used to work as a data scientist at a railroad, I would honestly never use PCA because you completely lose any interpretability unless you have just a ton of features and it doesn't really matter what what those features are or anything. If I had a couple hundred features, I might use PCA. But otherwise, like at my last job, if I couldn't explain why we were getting a prediction, like I wouldn't be allowed to do predictions. So it kind of depends on what industry you're in. If I just said it, the algorithm says we're going to use this much fuel this month, I have no idea why. Like, I wouldn't be doing it. So PCA is kind of a tough one. K nearest neighbors. So the problem that you have might be a good example of when to use K nearest neighbors. So you're looking at what you're looking at when one point is most similar to other points. So if you're looking at this person has the same education and the same job title and the same gender and same this, on average, how many people of all those categories make a certain amount of money. So like K nearest neighbors seems like it would probably work on this.
Okay. And what about support vectors? Do you think that might be something? You think that's something that might be a useful tool to use as well, a useful method?
Yeah, support vector machines. Yeah, this is a good question. Let me show you.
Yeah, because the part that I feel like I understand how it works in that it draws boundaries and tries to separate, different classes or different clusters from another.
Yeah.
Yeah. But for me, it's implementing it that I'm dreading.
Yeah. With scikit-learn, it's using the API is pretty. Once you do it a couple times, it's not too bad. It's just a matter of. So I kind of like referencing this. So interpretability versus accuracy. So we see that support vector machines, you can get pretty good performance, but it's not very interpretable. I found in my past experience, I would almost say random forests usually, I can get pretty similar accuracy with a random forest that I can get with support vector machines, but has a little bit added interpretability. I'm obviously a little bit more biased toward this side because like accuracy is great, but like you have to be able to kind of explain your results, in my opinion, like why you got something, because inevitably, like none of your models are going to be predicting 100% accuracy, and when you get one wrong, people are going to want to know why. And if you can say like, well, we were showing to use this much fuel this month, the past month, or we were going to have this many grain trains or this many trains, and we didn't see that many. Like it's a lot. It goes a long ways.
Okay. Yeah, I really like this diagram because what it showed me is the the two best ones that fit both criteria. It seems to be K nearest and random forest.
Yeah. Works out well for the K nearest. Yeah, and K nearest neighbors is pretty easy to like explain, because if you have a person that went to vocational school and everything, and they have this attributes about them, then you could look at how many people have met that same criteria, and how many of them went to college or had a salary above 50,000 or less than 50,000.
Okay. Oh, all right. That made me feel a lot better because I was thinking about, okay, should I use all of them? Should I use one? Should I use two?
I gotcha.
Yeah, but I guess what I'm hearing from you is it honestly just depends on the type of data you're faced with, how many features you have, and how, for lack of a better word, in depth you're trying to get with regards to interpretability versus accuracy.
Yeah, definitely. I actually have to run. I have another call I'm gonna have to jump on. Yeah, sorry to kind of end abruptly. But it was kind of a pleasure getting to talk with you for a minute. I'll post this recording on the Slack channel in case you want to like see it or anything. But if you have any questions about like interpretability, I'd love to feel free to reach out to me.
Yeah, no problem. I do have a question about just some of the hyperparameters, but I'll send it to you in Slack.
Okay, sounds good.
All right, cool. Thanks again.
Yeah. It was nice meeting you.
Yeah, nice meeting you too.
All right, see ya.